Organic chemistry makes fast cars. Without organic chemistry, we'd still be riding horses. Obviously we're not. We're riding horsepower instead. Cars changed the world. Up until cars arrived 100 years ago, the world hardly used any oil from the ground. Before cars was the age of coal, and coal drove massive engines of steam. Indeed, it was in the search for a lighter engine, a more portable source of power, that the car engine came about. But if you look at the way the car engine works, it's obvious that it needs a liquid fuel, not a solid. And it needs a fuel that burns fast enough to push the piston fast. Coal was no good, so they turned to petrol. Thus, the car moved the world into a new age. The age of petroleum.
Petroleum is Latin for rock oil. It refers to the fact that petroleum oil comes from under the ground. Sometimes it's referred to as mineral oil, to distinguish it from plant and animal oils, which are chemically different. They are triglycerides. Petroleum oil, on the other hand, is your basic oil, with nothing but hydrocarbons, mostly settled to the saturated forms, which isn't surprising. This stuff has been lying around under heat and pressure for millions of years.
So, like coal, petroleum oil is a fossil remnant of life in ages past. At the bottom of swamps or oceans, there's a slow build-up of dead organic material, mostly of single-celled organisms. If this is locked away from oxygen, it does not decompose, and anaerobic bacteria may reduce it to a waxy residue. Buried ever deeper, the sediments around it become rock, and with millions of years of heat and pressure, it will become what we know as crude oil.
Crude oil is a mixture of all sorts of hydrocarbons. Here are some of the products that come out of it. At the lightest, there is natural gas, methane. Then we have a whole range of other alkanes. Here's butane, also a gas or a liquid under pressure. Butane has a 4-carbon chain. Here's petrol, which is normally a liquid, but it evaporates easily. Here we're talking molecules with carbon chains in the range 6 to 12. Then we have jet fuel and household kerosene, say 12 to 16 carbons. Then diesel fuel, 16 to 18 carbons. Then lubricating oil, up around 20. Then heavy oil, and so on until the stuff really isn't liquid anymore, like bitumen. Above 30, you've got solid petroleum wax. Now, as well as the alkanes, there's also alicyclics, that's ring-shaped chains, as well as aromatics, that's the benzene family. And they're all mixed up in this cocktail of crude oil.
It's the job of the oil refinery to separate the crude into all its different parts. They do this by boiling the oil in towers like this. It's called a fractional distillation tower. In a way, it's like a giant coffee percolator. Most people know how boiling coffee will eventually boil off all the water and ruin the coffee. Of course, the coffee pod is designed to trap the water vapour, condense it and let it fall back in. But with oil, they boil it to deliberately separate the ingredients. These pipes, which lead off at various heights on the tower, extract the various hydrocarbons as they condense out of the boiling process. It's more complicated than boiling coffee or tea, but the principle is the same. Superheated crude at about 350 degrees C is pumped in at the bottom. Everything but the wax, bitumen and very heavy oil boils at this temperature. The vapours rise up the tower, cooling as they go. They condense in order of their boiling points. So lubricating oils condense just above the bottom, heating oils a little higher up, kerosene higher still, then petrol, and finally, at the very top, the lightest parts are drawn off as gases like butane, propane and methane. Thus, the crude is distilled into its fractions.
But this is only a beginning, because refineries quickly discovered that the amount of petrol which they could get straight out of crude wasn't enough for the growing number of cars. Most of crude refines into heavy oils, and in fact, they found they had too much of the heavier stuff. So obviously, the next trick to learn was how to take the surplus of heavier oils and break them down into the smaller molecules which make up petrol. They learned how to crack the long carbon chains into shorter ones.
The catalytic cracker is the heart of the refinery. In here, a little pressure, heat, and the presence of aluminium silicate cause the heavy oils to break down into molecules the size of hexanes and octanes, which are the basics of petrol. This at least solved the supply problem. But cars were getting more sophisticated.
You can get more power out of an engine by running it faster or by raising the compression ratio. But this also means that the rate at which the fuel burns becomes very important. Too slow and you'll lose power and overheat. Too fast and it will knock. Unlike the heavy, low compression engines of yesteryear, a modern car is very fussy about the kind of petrol it uses.
Knocking an engine is to be avoided at all costs because this is the sort of damage it can do. Instead of the fuel exploding smoothly to push the piston down on each stroke, it goes off fast and sharp and wrecks it instead. Straight carbon chains burn fast and branch chains and rings burn slower, so the petrol we buy is a mixture, a blend of hydrocarbon shapes that is judged to be right for the engine.
So the third important activity of the refinery goes on in the catalytic reformer. In here, straight chain hydrocarbons are reformed into branched and ring shapes, which burn slower. This reformed stock is then blended with the straight chain alkane stock and stored for sale as petrol ready to be used. The different burn rates are classified as octane numbers. The fuel in question has its burn time compared to a standard rate labelled 100 octane and is numbered accordingly. For example, unleaded fuel is around 91 octane and lead replacement is around 96. So lead replacement with the higher number is the slower burner of the two. And since reforming costs money, the fuel with the more complex mix of hydrocarbons is higher in price. The oil refinery is vital to our modern lifestyle. A lifestyle which offers more energy to use than at any time in history. It also runs us headlong into a massive problem.
Consider these figures. 40% of the world's energy comes from oil. In fact, 63% if you add natural gas, which is also classed as a petroleum product. Add coal at 27% and you get 90%. 90% of the world's energy comes from burning fossil fuels. Of course, there's no doubt that these fuels have improved the quality of life over the last century. But the vast scale of their use now threatens us with air pollution and even global warming.
And the scale of petrochemical products has another dimension. In an earlier episode, I mentioned that burning alkenes, the family of double-bonded hydrocarbons, could be considered a waste. And I mentioned that ethene gas is the raw material for polythene plastic. Well, this is just the tip of the iceberg. Have a look at all this. The oil refinery supplies alkenes, alkynes, aromatics, and the lightest alkanes as raw materials for all these products. And you can easily see, even though I can only fit a few examples on my bench, how they represent products we use every day of our lives.
So the petrochemical industry, with the oil refinery at the heart of it, is not only responsible for the bulk of our fuel, but also for the raw materials of solvents, paints, glues, dyes, plastics, perfumes, fibres and cloth, fertilisers, pesticides, drugs and explosives. More and more, we live in a petrochemical world. The benefits are obvious. Our present lifestyle depends on them. Yet once again, there are problems of scale.
In 1962, the biologist Rachel Carson published a book called Silent Spring. In it, she pointed out how dangerous the wholesale use of pesticides, particularly the chloroalkanes, could be. These chemicals killed creatures other than the insects intended. They sterilised the ground, and they were suspected of causing cancers in humans. The book sparked a huge debate about how we should use chemicals, and that debate has gone on ever since.
The debate was intensified not only by the effects of large-scale usage, but also by outright accidents. The oil industry itself struggles to overcome the bad press generated by spills like this. Perhaps the worst case of a chemical accident was thalidomide, which produced children with no arms or legs. Because of results like these, science began to acquire a negative public image. Government started to legislate to try and ensure human safety.
So chemical corporations are now very aware that public and environmental issues must be considered when getting the design of a new product right. And what may be the perfect solution to a problem on a small scale may become much less than perfect on a large scale.
Look at plastics. They litter our roads and beaches, virtually unchanged by weather or decay. Plastics, generally speaking, simply aren't biodegradable. This is a problem, even when they're disposed of at the rubbish tip. Modern rubbish disposal is more problematic than in the pre-plastic past because much of this stuff will not decompose. Recycling, the best alternative, requires buyers who can use this sort of material. Unfortunately, many companies are not geared to do that. Plastics are great, but they also have this difficult side.
Remember though that science is a powerful tool. And while science has created some problems, it has also helped to solve them. Look at cars. The modern car is lighter and more fuel efficient. With a computer controlling the engine and a catalytic converter on the exhaust, it puts out less pollution than ever before. And there are all sorts of experiments being tried to use non-polluting sources of energy.
But with less than 2% of our energy supplied by devices like these, we will still be in a petrochemical world for some time. Since public safety only follows public concern, understanding these issues will be crucial to our future.